In this lecture presentation, we will define work and power in scientific terms and discuss eventually how work is related to energy. So oftentimes we think about the word work in terms of I have to go to work or I have a lot of work to do, meaning maybe I have to do a lot of homework or I have to clean the house or something of that nature. So we want to be more specific and define work in terms of more scientific terms. So as we talk about work, it's going to turn out that work is closely tied to energy, and there's many different types of energy that we can discuss. And so it turns out that as we talk about different forms of energy, which we're already familiar with, that if something has energy, that means that it has the ability to do work. And so that's going to give us sort of an idea of where we're headed in terms of how energy and work are connected with one another. So we'll define work in just a moment, but if we think about the different forms of energy that we are familiar with just from, basically just elementary school all the way up through high school, some of the ones that we often see or talk about are electrical energy, light energy, thermal energy or heat, the way we think about heat, chemical energy, which is related to the food that we consume and then we're able to actually function in terms of our bodies, and then mechanical energy. And so we've already talked a little bit maybe in the past about electrical energy and light energy, but right now we're going to focus mostly in the next couple lectures on mechanical energy. So here's a picture that sort of shows how these different forms of energy can be transferred from one form to another. But there's also a nice PhET simulation that shows this as well. And so we have the different forms of energy here. So the little blocks with the E in them are different forms. And then the color coding on here is telling us what types of energy that we actually have. So I'm going to go ahead and I'm going to hit play on here. And that's going to allow this, I'm going to open up the water, a mechanical energy going in from the water. That mechanical energy is causing the rotation of this wheel, and then that wheel is connected to another component, which you can't see behind here, which is converting that mechanical energy into electrical energy. And that electrical energy, some of that electrical energy turns into thermal energy, which is causing the light bulb to get warm. And then some of it is also turning into light energy. So we've got energy coming out from basically this water that's falling, causing the wheel to turn, also mechanical energy, converting that into electrical energy, and then converting it into heat and light. So we've got lots of different forms of energy here that are being converted back and forth. So here we have another PhET simulation. It's the same PhET simulation, but you can adjust what types of sources you have for the energy, and then what you actually have that's doing the conversion, and then the different types of processes that you have afterwards. So let's go ahead and hit the play on this one. So I have light energy from the sun. It's hitting a solar panel. When it hits that solar panel, that light energy is converted into electrical energy, and then it's connected to a light bulb, so it's connected back into light energy and a little bit of heat, right? So there was a little bit of thermal energy that went off of that. So this is a different type of a light bulb, and this type of a light bulb, of course, doesn't produce nearly the same amount of heat as a traditional light bulb that we saw in the last case. So again, different forms of energy being converted from some starting energy to some ending energy. And then finally, here's another one. So here I have thermal energy. So when I start this, put heat in, it's going to cause steam, and that steam will cause the turn wheel to turn mechanical energy, converting into electrical energy, and that electrical energy is then converted back into mechanical energy, which causes the fan to actually rotate. So the one type of energy that we didn't see here is chemical energy, and so if you wanted to, you could go to the PhET simulation, which is PhET energy forms and changes, and you could actually put a bicycle here for the source, and a person would be riding the bicycle, and you have to feed them, so you have to give them chemical energy for them to then be able to essentially it's the wheels of the bike are then tied to this wheel that turns and converts the energy into another form. So, the idea here is we can see that there's many different forms of energy, and those different forms of energy can be converted from one type into another type and back to the original type in some cases. Okay, so we know we have these different forms of energy, but we don't know what the definition of work is yet. So the scientific definition of work is that work is force times distance. Now, this is a very general way to write work, and most of these lectures are on conceptual physics, so we're not doing a whole lot with looking at things in more complicated ways. So when we say that work is force times distance, this is the force that's being applied along the direction of the displacement, or the way that the object is actually moving. And so I'll talk a little bit more about that when we look at an example. So in general, work is force applied times the distance that the object moves in the direction that that force is actually applied, or in the opposite direction. It could also be the case. So in terms of units, the units for force are newtons, and the units for distance, our standard units in physics, are meters. So if you multiply a newton times a meter, you get units of what are called joules. So this is a defined unit. And so our work units are going to be in units of joules. So a couple of things that we notice about work. The first thing is that in order for there to actually be work done by a force that's being applied, there has to be some movement of the object. So if the object is sitting still, like you had a big crate, and you're trying to move that crate, and you push and you push and you push, and that crate does not move, the work that's being done by that force that you're applying is actually zero. There's no work being done. That doesn't mean you're not going to get tired from trying to move the crate, but the work that's being done on the crate by the force that's being applied, if that crate does not move, is zero. And as I alluded to earlier, only the part of the force that's parallel to the motion does work on the object. So you could be pushing on an object at some angle, but only the component or the piece of the force that's actually helping it move or hindering its motion is actually doing work on the object. The other forces are not actually contributing to the work. Work is also a scalar quantity, so it does not have direction. But having said that, work can be positive or negative, because scalar quantities, which are just numerical values without direction, can still be positive or negative. The work is going to be a positive value if the force that's being applied is actually helping the object move along the direction of the motion, and the work would be a negative value if the force that's being applied acts in the opposite direction that the way that the object is moving. So an example of positive work would be if you are pushing a crate across the floor, that's positive work. An example of negative work is that if that crate was on a rough surface, there could be some friction, which is opposing the motion, and the work that's done by friction is negative. It's not helping the object move, it's actually hindering its motion. And we're not going to talk a lot about the fact that work can be positive or negative, but I did want to mention that that can be the case. So let's look at a really simple example. So we have Juliet pushes a large crate that has a mass of 1 kilogram, and 1 kilogram is equal to 10 newtons. Remember, weight is mass times gravity, across the level surface with a force of 3 newtons, and she pushes it for a distance of 2 meters. So here's our force that's being applied. It's being applied parallel to the motion. It's not at an angle here. And this distance that the crate is going to be moved is 2 meters. And we want to know how much work is done on the crate by this force from Juliet. And we're going to ignore friction in this case. So before we go too far into this particular problem, we should think about, are there any other forces that are acting on the crate? And of course, one of the forces that are acting on the crate would be the force of gravity, or the weight, which acts vertically downward. And also, because the crate is sitting on a surface, there's actually a contact force or a normal force. Now, in our example, this normal force is going to exactly equal the weight because the crate is only moving along the horizontal direction, and so in the vertical direction, those forces are going to have to cancel. There's no acceleration or movement in the vertical direction. So these two, the normal support force and the weight, actually would cancel each other out, and the net force on this object is this 3 newtons, which is acting to the right. So according to our definition of work, which is force times distance, the force that's being applied is 3 newtons. The distance is 2 meters. And so there is a total of 6 joules of work that's being done. Now, the weight is another force that's acting, and this normal force are also acting, but they do not contribute to any work being done in this crate because those forces are perpendicular to the direction of the motion, not parallel. So they cannot contribute to any work being done. They're not actually helping this object move from one place to another. So the total amount of work comes from just this 3 Newton force and the distance that that object actually moves. All right, let's think of another example. So here I have Romeo, who lifts his physics book, also a 1 kilogram physics book, so a total of weight of 10 newtons. And he lifts it from the floor above his head for a total distance of 2 meters. And he does this at a constant speed. We want to determine what is the work done by Romeo in lifting the book. So obviously, if Romeo is going to lift the book, he's going to have to apply a force in the upward direction. And we need to know how much force he has to apply. I think everybody would agree he has to apply at least 10 newtons in order to lift this object up. So one of the keys here is that Romeo lifts the textbook, the physics book, at a constant speed. And so if something is moving at a constant speed, that means it has no acceleration, and it means that the net force on that object has to be 0. So the net force on this physics book has to be 0, and so that means that the applied force, which is acting up, plus the force of gravity, which is acting down, which is negative, has to equal 0. So Romeo is going to have to apply a force of 10 newtons acting directly up. So we now know what that applied force is, and we know that eventually he's going to take that book and lift it all the way up 2 meters, and so the direction of the motion is in the vertical direction. So the applied force and the displacement, or the direction of the motion that it travels, are both in the same direction. That work is going to be a positive value because you're actually helping the book move. So the work done by the applied force is just the applied force times the distance. The applied force is 10 newtons, and the distance is 2 meters. So force applied, distance, and it gives us 20 joules. So this is similar to the last example that we looked at, except in this particular case, the force is being applied in the vertical direction, but the displacement, or the motion, is also in the vertical direction, so that force does do work. We could also ask the question, is there work done by the gravitational force? So this is kind of not a weird question, but a little bit harder question. The force of gravity is actually not helping the object move, but we know that if for some reason that Romeo lifted his book all the way up to here and then let go of the book would fall back down. And as the book fell back down, work would be done by gravity. So on the way up, work is actually done by gravity as well, but the force is in the negative direction and the displacement is in the positive direction. So gravity is actually doing negative work here. So we mentioned the fact that the work can be positive or negative. In the first case, where the applied force is doing work, it's actually helping the block move upward, versus gravity, which is actually hindering the motion. So as Romeo lifts the book, gravity is actually pulling back down, And so it's hindering the direction of the motion. So Romeo has to actually overcome that force of gravity, or at least apply as much force and do as much work to allow that book to move at a constant speed. So work can be positive or negative. Most of the examples that we're going to see, the work would be a positive value because the force is actually helping the object move. All right, suppose we go back to Romeo in that last example, and we say Romeo lifts his physics book from the floor above his head for a total distance of 2 meters. So that's the last example. Romeo then holds the book above his head for 5 minutes. How much work is done on the book by Romeo in this case? So this is a harder question to think about conceptually because I think everybody would agree that you lift the book above your head. All right, that's great. But then you have to hold it there for 5 minutes. Your arms are going to get tired, right? So you would think that it would require more work to lift the book up and then hold it above your head for 5 minutes versus just lifting the book up and holding it above your head. But the answer is that it's the same amount of work in both cases. And the reason for that is because once Romeo holds the book above his head and he just holds it still, there's no more work that's being done on the book because the book is no longer in motion. There's no longer any displacement. So there has to be both force applied and some displacement for work to be done. Now, just because there's no work done doesn't mean that your arms aren't going to get tired. So inside your body, you've got work being done by your blood to pump that blood to your muscles and so on. So we have to make sure that we're defining the question correctly. And the question is the work that's done on the book, and the work that's done on the book would be the same. So oftentimes you see these questions where, what happens if you change one of the variables? What's the end result of another quantity? So here we have work is done in lifting a barbell. How much work is done in lifting a barbell that is twice as heavy, but lifting at the same distance? So one of the ways that we can approach this is to just give some initial values to the weight of the barbell and also to the distance. So let's say that the barbell weighed 1 kilogram and had a mass of 1 kilogram and weighed 10 newtons, and that the distance that it was moved was 1 meter. Well, the work would just be the force times the distance, so 10 newtons times 1 meter is 10 joules. If we now double the force so that it's 20 newtons, but keep the distance the same, force times distance, 20 times 1 is 20 joules. So the amount of work has doubled when the force has doubled or has increased. It's twice as much as it was before. So remember, if you have these kinds of questions, you can just arbitrarily pick some numbers to see how things would work out, and that'll give you how the quantity is actually changing in the end by looking at those numbers. But pick easy numbers. All right, you do work when pushing a cart with a constant force. If you push the cart twice as far, but with half the amount of force, then the work you do is, so is it twice as much, the same, half, 0? So let's do the same thing we did before. So we start off with easy numbers. So we apply a constant force of 1 newton for a distance of 1 meter. Then, if we push the cart twice as far, so twice the distance, but half the amount of force, oops, sorry about that. So we could calculate the work that's being done. So the work in the first case would be the force times the distance, which would be 1 joule. But now we push the cart twice as far, right? So the distance is twice as big, but with half the amount of force, so only 0.5 newtons. And we could calculate the work here, force times distance is also going to give us 1 joule. So we've increased the distance but decreased the force, and because work is force times distance, if you increase one by a certain amount and decrease the other by the same amount, then the amount of work is going to stay the same. As we talk about work, Another quantity that's often important to us is something called power. And power is basically the rate of doing work, or you could also think about it as the rate of using or producing energy. So you may have discussed previously that power can also be thought of in terms of electrical circuits. Power is current times voltage, and it's related to the brightness of a bulb. So in general, we're going to see that power has units of watts. And so if you have a 100-watt light bulb, it's going to be brighter because it's producing more energy than a 40-watt light bulb, for example. So the more quickly that you perform work or use energy, the more power that you generate. So it's basically a rate of producing or using energy. So we define power as the work divided by the time. In terms of our variables that we use, power is a capital P, work is a capital W, and then time is just T. And our units for work are joules, and our units for time are seconds. So power has units of watts. And again, this is something that we have encountered before just in our everyday lives in terms of light bulbs. And there's other things, certainly wattages of microwaves, but anything that's producing energy is going to have a particular power rating. So if we go back to the example of Romeo lifting the book above his head, suppose that he lifted that book above his head in a time of 0.5 seconds. What was his power output? So how much power did he have to put in order to lift that book? So we found previously that the amount of work was 20 joules. And we know the time is 0.5 seconds. So power is the work that's done divided by the time. And so 20 joules over 0.5 seconds is 40 watts. So the amount of power that was produced by Romeo in lifting the book was equivalent to 40 watts.